Hello, I'm Susan German. I'm one of your math facilitators. I'm here to try and give a quick recap over the last couple of weeks in our Math S109 class. One of the first things I'd like to talk about is one of the big ideas that we are trying to get across in this course, which is the key shifts in mathematics. When Common Core came out, it provided an opportunity for math teachers to have a greater focus on fewer topics, to link those topics and thinking across grades, and then pursue conceptual understanding. And that's the one that we're really going to kind of narrow our focus in on. With conceptual understanding, it's the idea of where students can grasp ideas in a transferable way. So we're wanting that big picture for our students. This brought to mind a question that I found in, I believe, Illustrative Mathematics. It was talking about purple paint. Purple paint, the perfect purple paint is made by mixing 2 cups of blue paint with 3 cups of red paint. How many cups of blue and red paint do you need to make 20 cups of perfect purple paint? Well, typically speaking, what we have right here below is what we do in our classroom, right? I've done this when I've taught math, is the kids apply some reasoning, 2 cups of blue paint to 3 cups of red paint, and they come up usually after some time with the idea that it produces 5 cups of paint, and that 5 cups of paint should be purple. Then they do some basic math. They take the 20 cups divided by the 5 cups, and they get the idea that they're going to need 4 batches of it. Then they go down one more step and they take the 4 batches times the 2 cups to get 8 cups of paint, and then they have the 4 batches times 3 cups to get the 12 cups of red paint. And then we stop there. Now, while that's a nice multi-step problem and it causes students to engage in some extended thinking, it doesn't necessarily by itself build a conceptual understanding of what proportions are, which is what we should be after as teachers in general, not just on proportions, but other topics as well. So if we look, we could have had students also show their understanding in different manners. Ask them, how many ways can you solve this problem? In our graph here, we graph blue paint versus red paint. So for 2 cups of blue paint, we have 3 cups of red paint. And if we keep going, then we're at 4 and 6. We're at 6 and 9. And then we're at 8 and 12. And notice that this makes a nice straight line, which eventually, when students look at graphing, they can realize that this line has a slope to it, right? And that this slope helps kids also think about proportions. Another way of taking care of it is just taking one of the paints, like blue paint, and comparing it to the total amount of paint produced, the purple paint. So notice we have, for every 2 cups of blue paint, we get 5 cups of purple paint, and we could keep working this out until we find that we have 8 cups of blue paint to 20 cups of purple paint, and then it's a simple subtraction. Could we also add another line here for how much red paint? Sure. Or we could group them by the boxes, which is what's demonstrated here, or we could use a table to get our understanding. By the time students are done showing as many possible ways that they could get the answer, it helps them build an understanding of the idea of proportions, that it's a 2 to 3 type proportion. And so they then start realizing that when we learn multiples and we learn all this other stuff, all those ideas are related. Now, while paint is not necessarily phenomena, what we studied in the class was a phenomena, one of them at least. Well, actually, kind of two, but one of them definitely, which is the life vest. So, and a phenomena is an event which is observable. And with math, using phenomena does a couple of things for us. And several of you mentioned this, that the students would be interested in knowing about the life vest, and through their interest in knowing about the life vest, we can also teach them some math. When we engage students in ways of mathematical reasoning, or to have to justify their answers with us, then through when they're trying to explain phenomena and they have to use math to help them justify their explanations, then we're getting to that deeper thinking, which is what we all want to happen in our classrooms. Moving from phenomena, so phenomena is that big picture. And by the way, I'm not trying to say that everything you do should be attached to a phenomena. However, if you see something and it makes good sense in your classroom, then by all means you should use it. But with a phenomena and kids trying to figure out the phenomena, then they have to bring tools or skills to the table. And that's what these mathematical practices are. And I put them side by side with the science and engineering practices in hopes that you see the amount of overlap between the two. So our scientists, our engineers, and our mathematicians are all doing things like developing and using models. They are arguing from evidence. So those are ideas, those are big skill ideas that everybody is doing together. But also notice that in the science world, here at number 4, analyzing and interpreting data. So that's definitely something mathematical and mathematical concepts being brought to the table. And then the other practice 5 here, using mathematics and computational thinking. So while science is science and math is math, there is definitely some overlap in the skill sets that each need that might help or might prove to have a way to help you as teachers integrate your subject matter. Lastly, one of the other big ideas that we tried to bring across in the last couple of weeks is the fact that using math and science or using engineering can help improve achievement in math and science. So the engineering experiences, which is what I refer to as the application of science and math concepts with judgment, get students to think mathematically, specifically. They also learn their math skills and concepts and skills a little more deeper by trying to solve an engineering problem. Like I said, they have to bring the application of their mathematical concepts and skills with judgment. So they have to bring that knowledge to the table. My personal favorite is by trying to solve problems, students discuss math and science concepts. I think that one is probably the most important. It's that social collaboration amongst the kids that helps them construct their knowledge. If everybody is trying to make meaning and they work together, typically the kids do a better job of helping each other develop their understanding than we do. And I say that as an experienced teacher. And what I mean by that is it's not that you are not doing your job as a teacher, but you know as well as I do, there are times that you say it and then the kid says the exact same thing and all of a sudden it makes sense. So we trying to harness the power of the knowledge of our classroom in order to get kids to talk to each other to develop a deeper meaning. So this should bring us to an end for our first little recap. I look for an email from me that's going to have a link to a survey to see if you guys are interested in having a weekly Zoom session and trying to find a time that schedules. It's by no means would be a requirement in any shape or form. It's just something that could be available to you, that if you're running into problems, you know that you have a way of asking a question and getting hopefully a little bit more immediate feedback. I've really enjoyed your posts. I've enjoyed the fact that you have tackled these problems and spent a great deal of time and effort and concentration in terms of trying to provide thoughtful thinking. Thank you for your time, and I look forward to finishing out the month.